two parts. The first part is solving separable differential equations. There's some differential equations that have x's and y's in them that you can solve. So remember when we had implicit differentiation, the derivatives had both x's and y's in them, and now the antiderivative are going to have both x's and y's in it. The vast majority of these you will not be able to solve, but if it's a separable differential equation, you can solve it. So here's an example. It's a derivative equation, but it has both x's and y's in it. So it should look something like implicit differentiation happened. So the process for undoing it is you're going to move the x's and the dx's and the y's and the dy's to the same side of the equal sign. So I'm going to go ahead and write this as dy dx equals x squared times y squared. I'm going to move the y's to the left and the x's to the right, just kind of arbitrarily. So dy divided by y squared equals x squared dx. Okay. Next, I'm going to take the antiderivative of both sides of my equation. So I'm going to do an integral of both sides of my equation. So I have the integral of dy over y squared is equal to the integral of x squared dx. I will have a plus c, but I'm only going to have a plus c on one side of my equation because the c is sort of arbitrary, so it doesn't really matter. I'm going to write this as y to the negative 2 dy. So if I take the antiderivative of y to the negative 2, I would add 1, so I have y to the negative 1 and divide by negative 1. And then on the other side, I would have x to the third over 3 plus c. Okay, now I'm going to find c. So I'm given this initial condition. I'm going to use that to find what c is. So I have negative 1 over 1 equals 1 to the third over 3 plus c. So negative 1 minus 1/3 equals c. So c equals negative 4/3. Then I'm going to write my equation as a function of y, which means I have to solve for y. I'm going to make sure that when I do that, my equation is a function. So I'm going to write this as negative 1 over y equals x cubed over 3 minus 4/3. Maybe multiply by a negative 1. So I have 1 over y equals 4 minus x cubed over 3. And so I know the reciprocal of y, so I'm going to write this as y equal to 3 over 4 minus x cubed. So now I have an equation, which if I take a derivative of it, I should get x times y quantity squared. Okay, here's a second example. Please pause the video and try it yourself, and then I'll go through the steps with you. So I'm going to multiply by y. Generally speaking, I like to keep the y side as simple as I can. So even though that negative sign isn't very complicated, I'm still going to move that with the x side. The reason I want to keep it as simple as I can is that eventually I will solve for y, so I want to make sure that I'm keeping it as simple as I can along the way. Okay, now I'm going to take the integral of both sides. So I have y squared over 2 is equal to negative x squared over 2 plus c. Okay, next up I'm going to find c. So y is equal to negative 3, so I have 9 halves is equal to negative 16 halves plus c. So c is equal to 25 halves. And then I'm going to solve my equation for y, making sure that y is a function. So I have y squared over 2 equals 25 minus x squared over 2. So y squared is equal to 25 minus x squared. And y is equal to plus or minus the square root of 25 minus x squared. Hey, that's a semicircle. But I need to decide whether I would use the top half or the bottom half of the semicircle. And since y is equal to negative 3 when x is equal to 4, it's going to be the bottom half of the semicircle. So it's going to be y is equal to negative square root of 25 minus x squared. You have to make sure that your answer is a function and that your initial condition is on your function. All right. Here's another example. Pause the video and try it yourself. And so I'm going to have dy over y is equal to 2x dx. Again, I like to keep the y side as clean as I can because that's the side that I'll be solving for eventually. Okay, then I'm going to take the antiderivative of both sides. So natural log of the absolute value of y is equal to x squared plus c. And then I'm going to solve for c. So y is equal to negative 3. Natural log of 3 is equal to 0 plus c. So c is equal to natural log of 3. And then I have natural log of the absolute value of y is equal to x squared plus natural log of 3. So the absolute value of y is equal to e to the x squared plus natural log of 3. So absolute value of y is equal to e to the x squared times e to the natural log of 3 because of this rule, e to the a times e to the b is equal to e to the a plus b. So sum of exponents rule. And then e to the natural log of 3 is going to be 3, so I have absolute value of y is equal to 3 e to the x squared, and that means that y is equal to plus or minus 3 e to the x squared. But then if I plug in 0, I should get a negative 3, so y would be negative 3e to the x squared. Remember, you want to choose your y so that it's a function, and you want to make sure that your initial condition is on your function. We'll do one more example. So sometimes when you move your dy's and dx's over, you have just a 1. So dy divided by cosine of x, cosine squared of y, is equal to dx. You can write a 1 there if you want to. Okay, then you're going to take the antiderivative of both sides. I'm going to actually write this, instead of cosine squared, I'm going to write it as secant squared y. Okay, now I'm taking the antiderivative, so the thing that gives me secant squared is tangent. Okay, now I'm going to plug in my numbers. So y is equal to 0, so tangent of 0 is equal to 0 plus c, so c is equal to 0. And then I'm going to solve for y. So tangent of y equals x, which means that y is equal to tangent inverse of x. So The process involves moving dy dx over to one side, taking antiderivatives, and then solving for y, making sure as you solve for y that both your initial condition is on the equation and that your equation is a function.